Ladies and gentlemen, welcome to the talk of this afternoon session. The speaker is Charles Bordenave from CNRS and Aix-Marseille University. He is the winner of the Frontier Science Award with Benoit Collin for their paper in Annals, which is eigenvalue of random lifts and polynomial of random permutation matrices. He will talk about strong convergence matrices, results, and applications. Please.
Thank you for the introduction. So yes, we are very honored to have this work, which was done a few years ago now with Benoit Collins. And so I will try to, many things have happened in this paper. So I will try to give you a kind of a general framework of this theory of strong convergence of matrices, which is emerging and has found many applications and probably will found more. So I don't expect you to be knowledgeable of anything in operator algebra on the matrices or whatever. So it would be more, my talk is more sort of a very lengthy introduction to this topic of strong convergence of matrices. Okay, so the first thing I will do is to try to define for you what are the relevant notion of convergence of matrix algebras, okay? So you can vaguely ask yourself this question. So you have a sequence of D matrices, even D equal to 1 is not completely uninteresting, which are of dimension n, okay? And you have a sequence of them, so n goes to infinity. And you would like to understand the algebra they span in terms of their, from a spectral point of view. So what would you like to do is to try to understand the spectrum of any polynomial that you can take in these matrices and they are adjoint, if they are not self-adjoint. Okay, so this is what I meant by a non-commutative polynomial. You may be interested by a kind of commutator or like kind of Laplacian type or adjacency type operator, whatever. You would like to understand the spectrum of all matrices, of all polynomials, of all matrices that you can span, that you can make by combining products, sums, and taking adjoints. Okay? That's your goal, and try to describe that in the large n limit. Okay, so operator algebra gives the proper framework to answer this question or to put it on a nice framework. So you can use the word of, you can consider a unital star algebra. Okay, so it is just an algebra with a star which acts like it should, okay? And you give yourself a linear functional tau, which is a linear map from your algebra to C, and such that your algebra is unital, so it has a unit. It requires that tau of 1 is 1, and tau of A star is just tau of A, of the complex conjugate of A, of tau of A, okay? And okay. And sometimes this is called the non-commutative probability space, okay? And the example that to connect with the previous slide you can have in mind is just you take n by n matrices and your trace will be your state tau, it's just a normalized trace, okay? And in the setting we are interested, we will assume that our trace is positive and faithful, meaning that tau of A star is non-negative always, and 0 only if A is 0. Okay, and with that you can define L infinity norm in your non-commutative probability space by taking lim sup of LP's norm of A star. Okay, and this will be a norm if under this faithfulness condition. Okay, this will be the most important object in the talk. So let's go through our example. Our first example was matrix algebra. So we have n by n matrices, our normalized trace. And what you define that is simply the operator norm, L2 from L2. Okay? And there are only two examples of non-commutative probability space I know. These are matrix algebras, and the other one are group algebras. So you take your favorite finitely generated group, or okay, let's say countable group at the moment. And for example, you can think of your group as being the free group or a fundamental group of some manifold. Okay, and you consider the group algebra, which are just the free module generated by your group, where you weight them by some complex weights. Okay, so that's finite sums. And this is an algebra when you consider then this product, which is only one you could think about. And the star is simply this operation. And the trace you take is simply, when you have an element in your group algebra, you just take the weight that you put to the unit of the group, which I will denote by E. Okay, and in fact, I don't really think about the group algebra like that. I more think about the group algebra as being an algebra of bounded operators acting on the L2 of gamma. Okay, so the way you can, there is a faithful representation through, for example, the left regular representation. So where you associate to an element of the group of your group algebra, lambda of A, which will be the weighted sums of the lambda j, and lambda j, it is simply the multiplication on the left in your group. Okay, so you take a Dirac mass at an element h in your group, and you move it to a Dirac mass at element g times h. Okay, so this is the group algebra. And the norm, the way I define it from here, it again coincides with the usual L2 norm, operator norm. Okay, so in the example I'm considering, this norm, which will play a crucial role, is just operator norms. Okay, if you have questions, interrupt me. Okay, so now with that you can define two notions of convergence. The first one is the convergence in non-commutative distribution. So you are given yourself, as I said at the beginning, your sequence of matrices, for example. So they belong to some, let's say, Mn of C, and you have your normalized trace, and you have some target elements in your favorite group algebra. Okay. And you will say that they converge in non-commutative distribution if for any non-commutative polynomial, you have convergence of the trace to the corresponding trace in the limit. Okay, it's called convergence in non-commutative distribution. It's a basic notion in operator algebra. And the hero of this talk is this strong convergence in distribution, which requires that in addition to that, you have the convergence of the norm. Okay, so the convergence, so it's stronger than the convergence of LP norm in all LP, because the convergence in distribution already implies the convergence of the LP's norm, because when you take the LP norm of P is again some polynomial. Okay, so it's strong because you exchange a limit in P and N when you require the convergence in L infinity norm, and that's the crux of this matter. Okay, there is a small star here because in many settings we know that if you just have that, it automatically implies that. Okay. For example, if it's a group algebra of a group such that there is no non-trivial abelian subgroup in the commutator, then this condition implies that. Okay. Okay, so it's not. It was the first proof of strong convergence. Is a fundamental paper by Hagerup and Torbjörnsen, who prove that if you take a random Gaussian matrix, Hermitian matrix in dimension n, and you let n goes to infinity, so it's a random algebra, almost surely, with respect to the randomness of these matrices, they will converge strongly towards something which I do not describe. And it was 20 years ago, sorry. And still, there is currently not a single deterministic example of strong convergence, which is non-trivial. I will come to this point later. All proofs are made now. The theory has developed a lot. There are many more random matrices that where we can prove strong convergence for for many different group algebras or general non-commutative probability spaces, but they are all based on random construction. Okay, so me, I'm a probabilist. I come from random matrix theory. I don't do operator algebra. But okay, if you are not a probabilist, there are fundamentally important questions related to strong convergence, which is find deterministic example of strongly convergent matrix algebra. There are many matrix algebra converging in distribution, but strongly, I mean, for non-trivial example, it's very hard. Or, I mean, we don't know how to do. And in just July 1st, Ramon van Andel just wrote a survey on strong convergence. So if you are interested by the topic, after my talk, you can try to read this very nice survey. Okay, so the motivation of Agop and Tomlinson were working on operator algebra, and they solved some conjecture, 20 years old or 30 years old conjecture in operator algebra related to the exterior automorphism invariance of the reduced algebra of the free group. Okay, whatever. So, and since then there have been a lot of papers using strong convergence as a black box to prove nice results. So in spectral graph theory, which was the motivation of the paper with Benoit that I'm talking about today, on the cutoff phenomenon, which is a sharp convergence of Markov chains, on the Buzzer spectral cap conjecture. So a famous paper by Hyde and Maggie proving that there exist hyperbolic surfaces, compact hyperbolic surfaces, whose spectral gap is of growing genius, whose spectral gap converge to 1/4. There have been some application in matrix concentration inequalities. Another conjecture in operator algebra, which was the Peterson-Thom conjecture, has been rephrased in an important work by Ben Hayes as a statement about proving that some random matrices was converging strongly, and this was proved a few years after that. Okay, so there are applications on hyperbolic three manifolds, very nice recent work of Antoine Song on minimal surfaces. I'm currently finishing a paper on application to quantum ergodicity, and I think that there should be a longer list of application of strong convergence. Okay, so what I will for the moment my matrices were general matrices. Now I will focus to unitary matrices and more precisely to representations. Okay, so I have my favorite group finitely generated, so free group or a fundamental group of a surface, for example, an hyperbolic surface, and you take a unitary representation of dimension n. Okay, which we denote pi, so it should be okay. So pi of G is a unitary matrix and it is a morphism. And when I take an element in the group algebra, I can look at its image by the representation, and it gives me a matrices of dimension n. Okay. And if I want to connect to my previous setting, I have the generators, and I define my ice matrix as being the image of the ice generator of gamma by my representation. It gives me a collection of unitary matrices, and I want to understand their convergence in distribution, strong convergence. Okay? And and when I write to connect with polynomials, if I take a polynomial in this group elements by the morphism property, I can write that as an image of some element in the group algebra of my unitary representation. Okay, so this polynomial, instead of speaking about for unitary representation, instead of speaking about polynomials in matrices, we just speak about image of group elements of the group algebra by this unitary representation. And every time that I give you an element in the group algebra, I have an n by n matrix. Okay, so now I can rephrase my convergence in distribution and my strong convergence. So the strong convergence The convergence in distribution, sorry. So Vi are my image of my generating set by my representation. So the convergence in distribution is just towards I will probably be considered case where the convergence of my representation converge to the group algebra or to its okay to the regular representation. Okay, so I will say the fact that this Pn of Gi converge to the lambda of Gi in distribution, it's equivalent to the triviality of the character, meaning that for any group element, the normalized trace, which was my state for n by n matrices, converge to the state of G, which is 0 if G is different from the unit of the group, and 1 if it's a unit of the group. Okay, so this convergence and non-commutative distribution do not depend on the choice of S. It's a property of the representation, of the sequence of representation. And the strong convergence is a strong convergence, so it's the convergence of the operator norm of the image of my unity representation to the image of the operator norm of P in my group algebra, which I can write like that. Okay? And again, these two notions of convergence, they are independent of the generating shades you choose. So it's really a property of the representation. You have a question? Okay. Basic example. I did not give you an example yet. So so if you take gamma to be ZD or SLD of Z, or okay, you could take the quotient map. N is an integer, so you can take the quotient map. Okay, the Z over n power D, or you can go into SLD of Zn, and just consider the representation, which to an element in one of those groups maps the multiplication operator by G mod n. Okay, it's a unitary representation of dimensions, the cardinal of these groups. Okay, and it converges in distribution because as n goes to infinity, if you take a finite word, you will never see the mod n operation if G is fixed. Okay, the normalized trace, as soon as the length of G will be less than n, the normalized trace of pi n of G will simply converge to 0 or 1, depending on whether or not G is 0 or 1. G is a unit, is 0 here, it's the unit of the group or not. Okay, so in this case, a basic example of convergence in distribution. Okay. An easy exercise is that if you converge in distribution toward your left regular representation, then 1/2 of the bound that you need to prove strong convergence follows from just the convergence in distribution. Okay, so the limit of the norm is at least the limit of the norm of the limit. It's a kind of Fatou type argument. Okay. And another, not so easy, but not difficult either, exercise is that if the group has sub-exponential growth, then convergence in distribution implies strong convergence. So when I was speaking about no example of non-trivial example, I was thinking about, let's say, take gamma to be a non-amenable group and find some sequence of representation which converge strongly. For example, for SL2 of Z, you do mod n operation. Does this representation converge strongly to the regular representation of SL2? I don't know. For SL4, I know it does not. For SL3, it's conjecture not, but for SL2, it should, but I don't know. There is no. Okay, ZD, it's amenable, so it's not interesting. Okay. Especially to get closer to the paper, what we looked at are special representation, which are permutation representation, where the pi n of G, where we are, where the pi n of G, there are permutation matrices. There are not any unitary matrix, there are permutation matrices. So then it defines the group action because you can represent your, for example, if you take if S is some generating set of your group, if you look at the image by a representation of constant function on S and 0 elsewhere, so this is the adjacency matrix of a graph, which is called the Schreier graph, which to a point X in this finite set maps through the vertex, through the generator G, the image of X by pi n of G, which is a permutation. Okay, so this is a Schreier graph. So it is defined by the definition, by the data of your group, a generating set, and this representation, which has to be a permutation. And then you have this Schreier graph. And these Schreier graphs, they are very nice graphs because they are covered by the corresponding Cayley graph on the group, which is defined by, with my operator algebraic notation, they are just defined as being the adjacency operator of this guy. Okay, where you connect a group element X to G times X, where G is in my generating set. Okay, so when you have when you have a discrete group action or permutation representation, you have the advantage to have a discrete structure, a sequence of graphs that you may want to compare to the corresponding K graph. And then you can okay, another example, so it's still in the same setting. And for example, if you consider an element in a group algebra which is a probability measure, okay, then the image of this element in the group algebra by your representations are just random kernels of random walks on the Cayley graph and on the Schreier graph, where you go from X to Pn of G of X with probability Pg. Okay, and all these random walks, they are covered by, if you have the random walk on the finite n space, it is covered by a random walk living in the infinite group. Okay, and the reversibility condition is just saying that P is self-adjoint, which is Pg minus 1 is Pg. Okay, and I can rephrase in this permutation action, representation, or group action, I can rephrase the convergence again in non-commutative distribution. The sequence of representation will converge to the left regular representation. This is equivalent to the convergence, the Benjamin-Ishram convergence, which is a notion of convergence for neighborhood, any finite size neighborhoods of my graphs toward, but my Schreier graphs converge for, if you fix any radius and let any ball around a typical vertex, you let the size of the graph go to infinity, you would like to say that this converges to the neighborhood, it's in bijection with the neighborhood of my Cayley graph. And this is equivalent. And again, it does not depend on the choice of the generating set. Okay, so this framework of unitary representation, which are permutation, it's essentially Benjamin-Ishram convergence, for those who know a little bit about graph theory and local graph limits. Okay, and strong convergence. So you have a problem when you have permutation, is that a permutation, the constant vector is always an eigenvalue, an eigenvector. Okay, with eigenvalue 1. If I have a permutation, the constant, so it's a trivial representation of, correspond to an irreducible representation of dimension 1, the trivial one. So what we want, when we speak about strong convergence for permutation, we have to restrict to an orthogonal of some subspace, which has at least to contain the constant vectors, which are a family of invariant vector space, which are considered as trivial. Okay. And this strong convergence, if you want to, I'm probability, so if you want to have a feeling of that, it's saying that you want, it's essentially, it's equivalent in many cases to the fact that all finite range random walks on your Schreier graph, all random walks, all PJ, for all choice of the PJ, so for all possible random walks that you can make on your Schreier graph, you want the spectral gap to converge to the norm of the corresponding operator on the limit object. That's equivalent to strong convergence. Okay, there's a very small assumption on gamma. Okay, let's put that under the carpet. Okay, so this looks like a daunting task to prove strong convergence. And there is one trick, one step, which makes it more accessible, which is which is called the linearization trick, which was found by Pizier, who was there this week. And roughly speaking, it says the following. It applies to much more general setting than the setting I'm speaking about today, but assume that you want to study, you have some favorite objects, which are here matrices, and you want to prove something about a polynomial in these matrices. Okay, like the spectrum or... Then this linearization trick is saying that, I think apparently it was invented by in electrical engineering. So it's saying for computing resistance in some networks. So assume that you are interested by, so for us, we are interested in the spectrum of polynomial in matrices. Instead of studying that, because it's nonlinear in the variables, which are the matrices you are interested in, instead of doing that, what you will do is you will study linear polynomials, okay, so just linear, this is linear in the VIs, but whose coefficients are matrices, okay? So this is a polynomial with a scalar coefficients, but it's a general polynomial. And this is a polynomial which is linear, but with matrix values weights, okay? And the general linearization trick is saying that if you know how to study, if you understand completely this, you understand in fact completely those, which looks more complicated. Okay, so in operator algebra, it was found by Pizier, and it is as the basis of many proofs in strong convergence, including the one I'm speaking about today. Okay, and so I can give you even algorithms. So now I specify to my unitary representations. So if you take an element in a group algebra, you take its image by any representation, then you have this general, if you give me the weights, so assume that the weights are supported in a ball of radius L, okay? For some, then, and you have some generating sets, so you take, which contains a unit, which is symmetric, and your generating set, so you count distance, so the support of that in the metric graph, in the Kelly graph, you look at the size of the support of this element of the group algebra in the Kelly graph with these generators, okay? So if you have, if you have an element in your group algebra which is supported in a ball of radius L, okay, then I can output for you matrices of dimension n, okay? So there will be one matrix for each element of your generating set. Okay, so the size of these matrices is given by L. Okay, it grows exponentially, but you can be smarter if you are more careful about the structure of this polynomial, of course, such that the norm you are interested in is exactly equal to the norm of this linear pencil, okay, which is linear in the sense that it only depends on the generating sets, up to a smooth function, an explicit function, okay? And it's an algorithm. So if you give me a few hours, if you give me your favorite polynomial, I will give you the ARs, okay? And in fact, so it's just an example. And in fact, for example, Pizier, you can say that my statement that strong convergence, saying that my convergence in norms, it's equivalent to the convergence in norms for all matrix-valued polynomials. Okay, so now I take elements in the group algebra where the Pj are not scalar complex numbers anymore, but they are matrices. And in fact, this is equivalent to just this convergence when the Pj's are supported on any generating set of your group. So this is, but okay, it's one instance of the linear trick, but it's a general philosophy. Okay, so now I will getting closer to the result of my paper with Benoit. We go into free group and permutation or representation of the free group, which will be random. So this is a free group with degenerators, okay? And okay, and these operators, they are free in the Voiculescu sense. Their distribution is, we know everything about the algebra they generate, those guys. We can compute the norms and so on. Okay, and if you have a matrix pencil, for example, if you take the element that we are interested in, this linear matrix valued pencil, they take this form. The lambda of GI are the free group generators, and if you specify the AI nicely, you can have, for example, just to have a feeling of what these objects may like. If you take the AI, which are 0, 1 valued, and you take them nicely, you can, this one could be the adjacency operator of such graph. Okay? So they are not exactly, so the free group was a tree, but this is a kind of flattened tree. Okay, and another motivation for studying matrix pencil, it is that there are a very operator algebraic way to represent covering tree. Let me tell you that. If you have a finite graph with d edges, okay, you can certainly write its adjacency matrix as, in terms of the canonical matrix, as a sum of, sorry, it should be 0 here, as a sum from over the d edges of E of ui. If the ith edge connects ui to vi, it also connects vi to ui. You can certainly write it this way, where the ai is E of ui vi. Okay? Just a way to represent the adjacency operator in a strange way. I just say it's a sum over all edges of or I run over the 4 edges, of this will be d equal to 4 here. I write it as a sum of 8 terms, and each term is the sum of a matrix, a canonical matrix EUV. Okay? And now I take this AI and I compose them by the free group generator, and I claim that this will be exactly like here. Exactly like here. This will be the generating. This will be the adjacency operator of a graph, and this graph will be the disjoint copies of the universal covering tree of the graph. Okay. So these linear pencils are interesting because they give directly access to lifts of graphs and universal covers. If you are in graph theory, this was your slide. Okay, and okay, so now we want to prove some strong convergence. So we need to define on the free group representation. There is nothing more easy. If you take any unitaries, the D unitaries prefer, you define that the GI's free generator, its image by P by N is UI, and this automatically, this uniquely extends to a representation of the free group. Okay? Since there is no relation in the free group, any collection of matrices, of unitary matrices, gives you birth to one representation. Okay, so what we will do, probably, so the UI will take them independent and uniformly distributed, meaning according to the R measure, on the unitary group of size n, on the orthogonal group, on the symmetric group. Okay, and I'm especially interested by symmetric groups because now when I have symmetric group, it will give me nice graphs, nice Schreier graphs of the type I just showed you. Okay, and okay, why not just, this is a standard representation of UN, just acting on C to the N, but you can also look, for example, at other representation of UN, and for example, look at the tensor product representation, which is simply that, so the UI are my favorite unitary matrices, for example, uniformly sampled, and I can define the image of the ith generator as being UI power some Q plus tensor product UI bar tensor Q minus. This is another representation, which is called tensor product representation for obvious reason. And this is a representation that you can see that as if you have kind of Q Q minus particles. Some of them are charged negatively, the one with the bars. And instead of following one particle, as in the standard representation, so Q plus is 1 and the rest is 0, you follow many particles at the same time. Okay? Okay, or you can take other irreducible representation of UN, and this one is not irreducible, but you can decompose it into irreducible representation. Okay. So these are the objects we want to study when the UI are random. Okay? So we are studying a random representation of the free group. And a digression, I told you it was a very lengthy introduction. A digression, if you do quantum information theory, which I do not, when Q minus is Q plus, this is interesting because it defines quantum channels, which are completely positive trace-preserving linear maps on matrices, acting on matrices. So to be more precise, so if you take any sum of pi is equal to 1, you take ui to be unitaries. If you do sum of ui, pi ui tensor ui bar, so this acts on Cn to C to the n squared, which is isometric to matrices. And so if you look at how this matrix acts on matrices, it acts by conjugation and weighted sums of conjugation. And this is one example of a quantum channel. Okay? So, and these quantum channels, and especially random quantum channels, they have been studied famously by Hastings and Arrow, PCA, and I can make some advertisement for former PhD students, Sarah Timagel. Okay, so it's very incomplete list. Okay, so let's come back to our problem. So now I will state the first theorem. So you have D independent and R distributed matrices on UN or orthogonal group. So unitary group, orthogonal group. I take my tensor product representation. Okay, so this tensor product representation is not, so if Q plus, okay, when Q is the sum of the, if Q equal to 1, it is a reducible representation. The standard representation will be irreducible, but okay, in general, for example, if Q plus is Q minus, the identity, the constant vectors is preserved, so it's not irreducible. So since Weil, we know perfectly well the invariant subspace of such representation, so which is the space of the subspace of Mn of C power Q of Cn power Q, such that which is left invariant by all these matrices. Okay, we know exactly what it is, and I don't want to describe it, but so we will be interested by what happens to this representation on the orthogonal of this invariant subspace. Okay, and you have the following result that so my UIs are distributed with probability 1 on the orthogonal of this invariant subspace, which is completely fully described. This random representation converges strongly toward the left regular representation of the free group. Okay, so, and I repeated the definition. Okay, so, and this is known for Q equal to 1 as a consequence of, so just standard representation, as a consequence of Agerup and Torbjornsen theorem. It was proved by Collins and Mal. Then with Benoit, we show that this is true for any Q. And then the upper bound we get in Q just got improved until this n power 1/3, which is not optimal anyway. So, but okay. So there is some challenge to take representation which are of higher and higher dimension in an attempt to reduce the randomness under which we know how to prove strong convergence. Okay, and this is this awards paper. It's about random representation, which are permutation. So you take an independent and uniformly distributed permutation matrix now. You consider your tensor product representation. It's real, so it's just okay. You know very well what is, if you know a little bit of representation theory, you know how to describe the invariant subspace. And we proved that on the orthogonal of the invariant subspace with high probability, you have convergence, you have strong convergence. Okay, We proved Q1 and 2, and probably better than Q of order 1, but there was a very nice new proof, new type of argument in this paper, which was pushed using a lot of representation theory of symmetric group in a very nice paper by Ewan Cassidy to Q less than n power 1 over 12, which is very impressive. Okay, and here is an application of what was the main motivation of our paper. It was to address this generalized Allen conjecture, which is, so this is my base graph, I fix it, and this is a two cover of my base graph, and this is the universal cover of these two graphs, okay? And there is one way to, when you have an n, this is a two cover. If I have an n covering, in the same way that, I should have written it, in the same way that I told you that I could write, this is my base graph, I can write the universal cover in this way with the free group generators. An n cover can be always written as a sum of these tensor independent permutations. Okay? So if we take this permutation uniformly at random, we get a uniformly sampled random n covering. And we could prove that on the orthogonal of its trivial eigenspace, invariant subspace, the operator norms converge to the operator norm of its universal cover. Okay, and it works for the adjacency operator or any other operator you may like, because we can take any polynomial. Okay, and this was is closely related to Allen's original conjecture in the 80s, which was proved by Joe Friedman, which was corresponding in this framework when you take G a single vertex graph and A the adjacency operator, and you have some bouquet of vertices along. Okay, so this is a kind of super Friedman theorem. Okay. Okay, so I mentioned all my other people work in asymptotic statements. In fact, all these theorems if you go into the proofs and the statements, they are, in fact, we prove quantitative bounds. Okay, so we know it's like quantitative probabilistic bound for each n. Depending on, you take your favorite polynomial, which could be matrix valued. So it's in terms of all parameters of the problem, which are the number of free group generators, the dimension of the matrices you put here, and the size of the support of this guy. Okay, I will not go into that because it's a general audience talk, but okay. And okay, that's free group, it's nice, but what about other groups and random representation of other groups? So now there is a long list. So we did the Cartesian products of free groups. We did, this was related to this Peterson conjecture we solved, but okay, I don't want to speak about that. But there is also this right angle arcing groups, for which we know how to build some random representations. The existence, so it's random construction, it's not the uniformly sampled random representation or R-distributed representation of the right angle arcing group. It's some random construction which proves that there exists some unit sequence of unitary representation converging strongly to a regular representation of any right angle arcing group. There is a recent paper about this time a uniformly sampled random representation of surface groups. It's a very recent and beautiful paper by Puder, Maggie, and Valandel. There is a non-constructive but existing result of for all fully residually free groups, which are groups such that any subset of any finite subset of group element can be injectively embedded by an homomorphism into the free group. So, for example, surface group, right angle arcing groups, and maybe not Cartesian product of free groups. Okay, and okay, and there are also surface group are fundamental groups of surfaces, hyperbolic surfaces. So, in fact, you have a kind of dictionary where you can lift this strong convergence statement in terms of bounds on the spectral gap of a Laplace Beltrami operator of random hyperbolic surfaces. Okay, this is the very nice work. This has started with the very nice work of Hyde and Maggie, and it's connected to the very nice works of Anantaraman and Monk on the Weil-Beta submeasure. Okay, and we know some groups we do not have strongly converging unitary representation. SL4 of Z was proved by De La Salle and Maggie, and it's conjecture that any group probably you cannot be strongly converging and having property T. So it could be that all SLD for D larger or equal to 3 do not have strongly convergent unitary representation. But at that time, I mean, me, I don't know. And okay, a comment. Strong convergence is interesting for two things. So I gave you an application like in random lifts. So it's interesting for the finite n object. But for example, the motivation of Hagerup and Torbjörnsen, the very first strong convergence result, it was to prove something about the limit algebra. So the fact that you can use the fact that you have some strongly converging representation to say things about the limit algebra. So it's always interesting to prove existence of strongly converging unitary representation for a new type of algebra. It will have automatically some nice consequences. And if your sequence is has enough, okay, so I don't want to be too vague. So okay, it's interesting on both sides. In the limit and for the finite object, it depends on your point of view. Okay, so I will give you a few ideas. In the remaining time, it will be very less not technical. So I will give you the trivial inequality. Okay. So again, strong convergence is about this convergence of operator norms. Okay, and you can linearize it if you want. You will probably. And the upper bound is always the difficult part. Okay. And it turns out that there are universal quantitative lower bounds, which I love, which goes under the name of Alon-Bopana lower bounds, and which would be in textbooks. So that's what I make some advertisement about them. So Alon and Bopana, Alon need no introduction. It was at the mid-80s that he discovered that. Okay, so now in modern language and in a super general kind of statement, we would say that. Assume that you have an element in the group algebra of my favorite group, gamma, which is, so this is matrices indexed by group elements, okay? And I assume that they have non-negative joint moments, meaning when I take trace, it's always non-negative. For example, just take P as the non-negative entries, like in adjacency matrix of graphs. So let's say you take a matrices which have indexed by group elements which have non-negative entries. And then you consider representation which have non-negative character, meaning that the trace of the character is always non-negative. Example, permutation representation. It's a permutation matrix, so it's a negative integer. Or my quantum channels, which are tensor product of two representations. Okay? So in particular, this applies to all graphs and to all quantum channels. Lemma, if you are in such setting, if you consider any invariant subspace of your sequence of representation of small codimension, in terms little O of n, then the norm of your finite n matrix is at least the norm of the limiting object for any choice. So you cannot beat this guy. So this random construction, it sheds a new light on strong convergence because you are trying to find finite n objects which are spectrally optimal, meaning that they match the universal lower bound which has to satisfy any representation with a negative character. So that's a big challenge. Okay? And okay, so this was a non-quantitative Alon-Bopana bound. You can turn out to quantitative. For example, you can get as a consequence of that. For example, with Benoit, we proved that if you take representation of the free group, I mean any permutation matrices or tensor products of unitary matrix, we have this bound, which is true. So the AI are matrices of dimension small n. We have this bound, which does not depend on small n, but you compare the norm with the unit, these are the free group generators, and you have a finite n volume correction, and it's universal. It does not depend on the choice of the UI, neither on the dimension of the matrices. So it's a universal Allen-Bopana bound, and it's quantitative. So the constant C, you can compute it. Okay, it's a good time to thank Naru Takaozawa, which taught us about this. It's a consequence of the fact that it's uniform in N, is a consequence of the exactness of the free group algebra. Okay, so okay, let me give you where does this come from, and how do you prove the upper bound quickly? So you have your polynomial. I told you the way I define my L infinity norm. This is the limit of the LP norm. So I'll put LK norm because I had already a P. Okay, so this is the limit of the LP norm. Okay, so I can write it like that. And this convergence in many groups, like free group, you can exactly give a convergence rate. Okay, so this is less than this. This is for any k. This is larger, but you can bound the difference on groups like hyperbolic groups and exact groups in a very precise quantitative way. Okay, and then to Allen-Bopana, then it's completely trivial. You take pp star power k. You look at the character. So I just expand it. Okay, that's the definition. And then you use that the trace of tensor product is product of trace. And you know that everything is non-negative here. So you just keep the element corresponding to the free group, to the unit of the group, which is exactly the term appearing here. Okay. So you have an exact lower bound, and you know that this is close to what you are aiming for k large enough. And then you just compare norm with trace, and you deduce this very simple bound. Okay, so that's Allen-Bopana. The upper bound, you have to do the same game, but in the other way. So now you have, for the upper bound, you are here, but now you have to take into account all terms. You know that the term you want to prove its dominance is corresponding to G equal to E. So you subtract it, you look at the sum over all G different from E of this guy, and you want to upper bound that. So you need to have combinatorial probabilistic arguments to upper bound that. I will just flash one key ingredient in all proofs I know. So I just kept this one because this is the one which is common to all proof I know, which are known so far. So we are interested by a random permutation, random orthogonal matrices, random unitary matrices. So you need to know how to compute expectation of product of matrix entries. This is called Weingarten calculus. This was the PhD thesis of the topic of the PhD thesis of Benoit Collins, my co-author. And so there are closed form formula for that, for each n, and you are interested by the asymptotic as n goes to infinity. And now we have very sharp and good understanding of the asymptotic of such expectations. It's quantitative in terms of the number of matrix entries and as the dimension goes to infinity. So this is the key probabilistic ingredient you need to assess, to do this proof. And then there are many other ingredients, but this is an ingredient which is common to, you need to be able to integrate over the R measure the matrix entries. Okay, some concluding words. What would be interesting is to include some deterministic matrices in the picture. It would allow to have many more interpretation. It would allow to have to grasp many more things, including some things in operator algebra that Ben has tried to explain me, but okay, it looks interesting. For me, at my level of understanding, it also would cover like representation of graph products of finite groups and objects like that. So it could be very interesting to include, to have strongly convergence results. I mean, comparison, it would be not limits, but like quantitative bound when you include some deterministic collection of matrices. I don't think that we have exhausted the list of application of strong convergence. Currently, I'm working on application in quantum ergodicity, but I'm sure that there are many more applications to find in your domain. If you have matrices of growing dimension, you may ask what you could get from. This is for example, if you think about random permutation representation, we have seen that convergence in this distribution is equivalent to Benjamin-Ishram convergence, so convergence of the local graph geometry. But strong convergence is stronger, as this name suggests, so it graphs slightly more. And so it graphs, for example, mixing times of Markov chains. So this was the previous work, but okay. So it's not clear, so there should be many other applications. If you want, maybe one of the most prominent open problem is what happens if you come back to, if you take random permutations, but now I do not see them as permutation matrices, but as element of the permutation group. Okay, and I look at the multiplication operator on Sn. Okay, so it's a matrix of dimension n factorial. Okay, so which acts by multiplication by my random permutation. So I'm asking whether or not, for example, I'm interested by the spectrum of the Kelly graph on Sn of d independent permutations. Okay, so there is a signature problem, so let's take them on the alternative group. Does it converge strongly to the free group elements? It's a major open problem. A thing which I love very much is it's still in this attempt to reduce dimension. Is everything is, as I told you, when you do Van-Gatten calculus, you have closed n formula, and then you take the limit as n goes to infinity. But you could also go the other way around in the same way that we did a little bit, that you fix the dimension of the Lie group, you take U3 or SU3, and you take a tensor product representation of very high dimension. Do you have freeness here? It should be the case. So I'm very bad at simulation, so this is my best attempt. You have, I took 3 matrices which are R-distributed on SU3. And now I take, I could not do more than 9 tensor products. Okay, so it's still a matrices of dimension 20,000. And then you can see that if you look at the spectrum of this large matrix, so they are only as a manifold, it has 8 degrees of freedom. Okay, so there are very few random variables here. There are 8 independent random variables roughly. Okay, and still you see that if you compare the spectrum of that compared to the spectrum predicted by free probability, there is a very good match, especially at the edge. So it should converge strongly. So it's completely different setting where you take a representation of very high dimension of a fixed Lie group. That's a dream, but okay, I'm not strong enough, but in Lie group algebras, but maybe some of you may try that. I think it's a very, very nice question. Okay, thank you for your attention.